Section 2, the theory of plate tectonics. Our key ideas, we're going to summarize the theory of plate tectonics. We'll identify and describe the three types of plate boundaries, list and describe three causes of plate movement. So how continents move? Again, remember the plate tectonics theory. It is a theory that explains how large pieces of lithosphere, called plates, move and change shape. Our surface on our planet, the outermost layer is called the lithosphere. It consists of the crust and a rigid upper part of the mantle. Underneath the lithosphere is the asthenosphere. The asthenosphere is a plastic, pliable, movable section right underneath the lithosphere. Kind of works like a conveyor belt, and it causes the lithosphere to move on top of it. So again, the lithosphere forms the thin outer shell of our Earth's surface. It's broken up into plates. They ride on top of the asthenosphere, much like wood floating inside of water. These plates can include continental crust, oceanic crust, or both. This picture shows the South American plate, so you can see where there is continental crust and also oceanic crust, where the South American plate is at, so it's a combination of the two. There are about 15 major plates that have been identified. There's a number of smaller ones, but the majority of the larger ones are found throughout the entire globe, and there are only 15 of them. Often, where plates are at, along their borders, there are major surface features, so mountain ranges or deep trenches can occur there. Scientists typically find borders between plates by studying earthquake activity. They also study the locations of volcanoes in order to identify plate boundaries as well. As you'll see, the plate boundaries do not necessarily all follow along continental margins or continental lines. For example, over here, if you look at the African plate really is much larger than the continent of Africa itself. It includes much of the Atlantic Ocean and parts of the Indian Ocean. The South American plate here, however, has a plate boundary right along its western coastline, and it follows the entire western seaboard of South America. So some of those plate boundaries do follow along the continents, other ones do not. So quick quiz. How do scientists identify locations of plate boundaries? Take a minute, think about the question, answer it. Scientists use the locations of earthquakes, volcanoes, trenches, and mid-ocean ridges to outline tectonic plates. The boundaries may be in the middle of the ocean. They may also be around the edges of continents or even within the center of continents. For example, on that last picture we saw, the Indian plate is pushing into portions of Asia. As that plate is pushing into the portions of Asia, you'll notice that the plate boundary is actually deep within the Asian continent. And as that plate is pushing in, it's actually creating the Himalayan mountains. The three types of plate boundaries are divergent boundaries, convergent boundaries, and transform boundaries. And usually there is some type of geologic activity that is associated with each type of plate boundary. So divergent boundaries. A divergent boundary is a boundary where two plates are pulling apart from one another. In this location where the two plates are pulling apart, there's magma that's rising from the interior of our planet. It cools and solidifies, creating new rock. Also along the center of that area where the two plates are diverging, there is a rift valley that forms. A rift valley is simply kind of a crack or a seam in the earth itself. Convergent boundaries. These are boundaries where two plates are pushing into one another. Where ocean lithosphere and continental lithosphere come in contact, there is what's called a subduction zone. The reason that there is a subduction zone is because the oceanic plate is actually has much greater density than the continental plate, so it slowly slides underneath the other one, or we call that subducting or sinking underneath the continental lithosphere. Where that occurs, you'll notice that heat and friction build. As heat and friction build, it's going to melt rock. That rock is going to eventually create pressure, and at some point that heat and pressure needs to be released. The Earth releases heat and pressure of internal magma through a volcano. When two plates that are made of continental lithosphere collide, because they're relatively the same densities, they actually push into one another and they just uplift one another. So where convergent boundaries occur, they have the two plates have similar densities, they're going to create an area of uplift. And then when we have two oceanic plates that are pushing into one another, because they're both relatively the same densities, however the density is very great, typically one kind of subducts under the other one. It kind of creates an underground or underwater trench, and then this trench may form island arcs. An example of an island arc that is formed on our planet due to this process is in the Caribbean areas, so around the Gulf of Mexico and kind of east of there as well. The islands of Cuba, Haiti, Dominican Republic, Jamaica, some of those islands are part of an island arc due to this process. So a quick quiz. Describe the three types of collisions that happen at convergent boundaries. Take a minute to do that. Collisions at convergent boundaries can happen between two oceanic plates, between two continental plates, or between one oceanic plate and one continental plate. And then also remember that where one oceanic plate and one continental plate meet, typically there's a subduction zone. Where two continental plates converge, we're usually going to have uplift, and then where two oceanic plates converge, usually there's a little bit of subduction and a trench forming. And island arcs can form off of this subduction zone. Transform boundaries. Transform boundaries are the boundaries where two plates slide horizontally past one another. When two plates are sliding past one another, a lot of times they'll get stuck. They'll kind of get caught next to one another. Pressure will continue to build as those plates continue to slide. The sudden release of that energy or sudden release of that pressure causes what we know as an earthquake. The San Andreas Fault is a perfect example of this in California, where two plates are sliding past one another. The two plates get caught up on one another. There's pressure that builds, and when that pressure is released, we end up with an earthquake forming. So that southern portion of California is notorious for these types of earthquakes due to a transform fault or a transform boundary. The mid-ocean ridge is also connected by a number of transform boundaries. Those are called fracture zones. Our plate movement is due to mantle convection. So recall that we have differences in densities that occur due to differences in temperature. Thinking back to when we studied weather and studied our atmosphere, we get differences in density due to the uneven heating of our planet. The equatorial regions heat up much more than the polar regions do. So at the equatorial regions of our planet, we get rising air. At the polar regions, we get sinking air. So it creates this big convection cell on our planet. The same thing happens within the mantle. So we get these large areas of convection, and these large areas of convection within the mantle help to drive this force of plate movement. the energy or the heat that actually provides the convection to occur comes from the core. So heat within the planet causes this mantle material to warm up. The mantle material that warms up becomes less dense. It rises up towards the surface where it's cooled. That cooler material becomes more dense, and it cycles back down into the earth to become reheated again. So inside of the mantle, we get this really large conveyor belt that occurs, causing the lithosphere on top to be transported. So if we were to boil a pan of rice, what type of energy transfer would we observe? And this is the similar process that scientists think is actually occurring within our mantle. So hold your fingers up. 1 for A, conduction. 2 for B, convection cell. 3 for C, radiation. Everyone should have a number 2 up for convection cell. So think back to that conduction, convection, and radiation lab that we did. We have this energy transfer that's happening due to the uneven heating of a fluid. Ridge push. So going back to this process of uneven heating. Newly formed rock at the mid-ocean ridge is warmer. Because it's warmer, it's less dense. As that rock cools, it becomes denser. As it becomes denser, it begins to slide down the slope that is created at the mid-ocean ridge. And this occurs between the lithosphere and the asthenosphere. The sliding rock exerts a force called ridge push. Which causes the plate that is out ahead of it, that has already been created, to continue to get pushed forward. This picture represents that. So we can see where we've got cooling rock occurring here. Again, it's happening between the lithosphere and the asthenosphere. That cooling rock is becoming more dense, and it is sinking, and it's pushing the rest of the plate that's out in front of it forward. So quick quiz, how may density differences in the rock at a mid-ocean ridge help to drive plate motions? How will density differences help to drive these plates? Alright, as they become more dense, this process of ridge push is going to occur where it's sliding down away from that less dense material. Very good. Slab pull. Slab pull usually happens where there is a subduction zone. So as we have plates that are starting to subduct into the earth again, it causes the lithosphere to cool and become dense. The leading edge of the plate begins to sink beneath the other one. And what it does is it causes a pull to occur behind it. The rest of the plate gets pulled along behind that area that's subducting. This process is called slab pull. And in general, plates that are subducting move faster than plates that are not subducting. And so scientists think that subducting lithosphere is a strong driving force for tectonic plate motion. They think a lot of this subducting is what's causing the plate movement on a global scale. So this picture right here represents that. It shows where a plate is sinking or subducting. as it's subducting down, it's going to pull all the rest of the plate behind it. So quickly, let's do this checking for understanding. As cooling rock becomes more dense, it begins to slide down the slope between the asthenosphere and the lithosphere. What process is this describing? 1 for ridge pull, 2 for slab pull, 3 for continental convection, or 4 for subduction? See a few people that have slab pull. This process is actually describing ridge push. Okay, so where we've got cooling magma becoming more dense, it begins to slide down a slope between the asthenosphere and lithosphere, pushing the rest of the plate in front of it. This is ridge push.
The Earth's crust is broken up into jigsaw-like pieces called tectonic plates. This map shows the major tectonic plates and their relative direction of movement. Notice that many tectonic plates include both continental and oceanic crust. Tectonic plates are pieces of the lithosphere that move around on top of the asthenosphere. Compare the thickness of the South American plate below the Andes mountain range to the plate below the oceanic crust. Mountain ranges that occur in continental crust have very deep roots relative to their height.